Okay, so a collision means that we have two objects that have the exact same index into the underlying array. So the first question is, do we actually really need to worry about this? Can we just find some simple way to handle this? Does it happen very often? So to answer that, let's talk about something called the birthday problem. Some of you may have seen this before, but let's consider we have n people with birthdays uniformly distributed at random. Turns out birthdays aren't typically distributed at random. There's a few days that people like to avoid. In the US, people try to avoid July 4th and December 25th and other days like that. So we don't end up with something that's perfectly uniform, but in general, fairly uniform. The question is, how large does n need to be before there's at least a 50% chance that two people have the same birthday, which would mean two objects collide inside the hash table? So that's the first question here. You could think of this as, we've got a bunch of people, a bunch of objects, and we're going to map those into a hash table of size 365. How many do I have to have before there's a 50% chance of collision? And before I insert a question here, I'm going to give you a little bit to work on. So let me give you some possible answers here. If I have n people and I want at least a 50% chance that any two of them have the same collision, how many? What value does n need to be? Well, some of these are fairly easy to eliminate. So if I have 367 people, I have a 100% chance of a collision. We know that from the pigeonhole principle. So if you were taking discrete math and you heard the pigeonhole principle and you thought you'd never use it, well, here's an example of using it. We can also eliminate fairly easily 184. I say we can eliminate that very easily because just picture inserting, that's about half of 365. Let's say you insert the let's say you're inserting the 185th person. Well, the 185th person is going to have a 50% chance by themselves of having a collision, which means, the 184th person had roughly a 50% chance. So, just those two together are going to give you an expected number of collisions of 1. So pretty easy to eliminate this one. You're going to have a much higher chance than 50% at 184 people. You're at 100% here. So you're really left with two options. And what might be surprising is that even at just 57 people, you have about a 99% chance of two people having the same birthday. And it only takes about 23 to have a 50% chance. So, I've been teaching this course for long enough to have done this, let's see, what is this? The 10th time. And I think all 10 times I've had at least two people in the class with the same birthday. Because I've, had a range of about 18 a couple of semesters, up to 46 people in this class before. When you get 46, I know there's a pretty good chance of having two of them with the same birthday. All right, well, let's move on to question 2 of the exercise. Let's say we have a hash table implemented using an array with 100 buckets. Let's assume that we have a perfect hash function, meaning that it generates hash values uniformly at random. What's the probability of a collision if we try to store 10 objects, 20 objects, or 30 objects? And we'll use a slightly more accurate equation than what I would normally use to compute like I did on this one. But since I didn't show you the equation I used for that one, you can kind of just ignore this note here. The equation we're going to use is this one up here. So if this looks a little cryptic at first, try to read it a little bit, try to answer this question, and then you can continue with the video after you've had a chance to try it on your own first. Okay, well, let's break this down into just sort of inserting first one item, then 2 items, then 3 items, and so on. So after you insert the first item, or when you insert the first item, what's the chance of a collision? Well, that's a 0% chance of a collision the first time. There's nothing to collide with. How about when inserting the second item? Well, it can interact, or it can collide with the one element out of 100. So there's only a 1 in 100 chance that time. How about when just inserting the third element? So ignore the first and the second. How about when we insert just the third element? What's the chance of a collision just on the insertion of the third element? Well, just when inserting the third element, it could collide with any of the two that are already in there. That's a little bit different than the question I'm asking up here, though. This is any collisions. So saying what's the percent chance when inserting the third element is different than saying what's the percent chance of any collision when inserting 3 elements. When inserting 3 elements, I have to take into account all 3 of these probabilities. So you could think of this as the probability of colliding, the probability of any collision is equal to something that sort of combines all 3 of these probabilities. Well, we just can't add these together, so it turns out that it's much easier to compute this as, the probability of any collision is the same as 1 minus the probability of no collision. And it turns out to be much easier to compute this one. So what's the probability of no collision? It means there was no collision the first time, no collision the second time, and no collision the third time. So the probability of any collision, and we'll say when inserting the first 3 items, is equal to 1 minus the probability of a no collision when inserting the first item times probability of no collision when inserting the second item times the probability of no collision when inserting the third item. And these are much easier to compute. The probability of no collision the first time is 100%. The probability of no collision the second time is 99 out of 100. And the third one is 98 out of 100. So if you notice, you can start mapping that to the equation up here. If we take this, that's essentially the probability of no collision. And we can estimate that with this exponential right here. So if I plug in our values, we would have n is equal to 100. X, this value here, is equal to 10, 20, and 30. And that's all we need for this part of the equation here is to plug in x and n. And when you plug in x and n, you get a 36% chance with 10 objects, an 85% chance with 20 objects, and essentially at 30 objects, even though you have 100 slots, there's almost a 100% chance that you've had a collision. And I think this plot here really sums it up nicely. We could take this all the way out to 100 items, and that's when you would have, a guarantee that you've had a collision. But, it does not take very many items before you're at roughly a 50% chance of a collision. So what does this look like? Maybe around, a little under halfway through there, so maybe 14 items or so, and you're at a 50% chance of a collision. So what does this mean? Collisions are going to happen, and they're going to happen a lot.